let me jump into the next session and let me introduce you to Federico Pecora, our invited speaker for today. Federico Pecora is a senior manager in applied science at Amazon Robotics. His research essentially lies at the intersection of artificial intelligence and robotics, and it focuses on combining methods from these fields to develop solutions with high impact in society and in industry. Federico's research looks at problems in concrete application settings, okay, as these often pose the most interesting and general research challenges, and addressing these challenges leads to better solutions for real applications. So with that, I'll hand it over to Federico.
All right, thank you so much for the kind introduction and for the context. The context is very useful for me because at this point, I don't have to convince you that multi-agent planning and multi-agent pathfinding and related problems are very important for Amazon and in general. I will try and do my best to explain to you why we are so interested and why we have funded this competition. Now, before I get into any real talking, I'm going to try and share my screen. All right, so once again, I manage a team here at Amazon Robotics. We call ourselves the Movement Science Team. We are one of several teams of researchers, in fact, applied scientists and research scientists, in fact, mostly applied scientists, who study problems or elicit research challenges that arise from our operations here at Amazon, and in particular the mobile robot operations that we have. Design solutions for them, and then interact and coordinate with our core software and hardware engineering teams here at Amazon Robotics to make those solutions into products and into reality. A couple of words on what Amazon Robotics does before I get into what we do in particular in my team. Amazon Robotics was formerly known as Kiva. In fact, it started off as a company called Kiva and was acquired by Amazon in around 2014 or 15, I believe. Long before I joined. I joined just under 2 years ago. And at the time, Kiva had developed some technology to essentially automate the movement of shelves, as you'll see, things we call pods today, around warehouses, so as to allow robots to move towards associates, people who are picking items, rather than people having to walk around a bunch of shelves to pick items. Now that company was purchased by Amazon, and since then Amazon has become our only customer. So Amazon Robotics is the sort of not subsidiary or the part of Amazon that produces robot mobility solutions for Amazon and for Amazon exclusively. And these robotic solutions are what essentially powers the network, or is a significant part of our capability in delivering products to you when you order them. So essentially, the magic that happens from clicking on the product that you want to buy to the delivery of that product is, at least in part, I should say, multi-agent planning. I say in part because, of course, there are many things involved. There's trucks driving around. There's airplanes. Amazon has its own airline. There are plenty of other processes in this flow. But the processes that involve mobile robots, and in fact also manipulators, as I'll show you in this presentation, are really at the core of it. And they are responsible for a lot of the efficiency that we can achieve. And that efficiency is key to keeping, of course, the price of delivery down on one hand, and the ability to deliver quickly down. So a couple of figures, first of all, so we sort of situate ourselves on what we're talking about. We have about 200 plus robotic facilities worldwide. It's more close to 300 by now. We serve primarily, so our largest deployments of robots are in North America and in Europe, or the North America and Europe and Middle East region. We also have facilities in certain parts of Asia, in Japan, for example. 75% of all our orders are supported by robotics. This is a very large number if you think about it. Amazon is an enormous retailer, and 75% of every order is touched by a robot somehow. And during this presentation, I'll show you what kinds of robots actually touch your order. We have 15 different robotic systems involved, from robots that move packages, to robots that move shelves, to robots that pick packages, that pick items, and so on. I'll show you a few of them. In total, we run the largest fleet of mobile robots in the world by far. At the time of preparation of this slide in particular, which goes into all of our presentations, this was 750,000 plus robots. Indeed, this is higher today, so emphasis on the plus here. We run so-called fulfillment centers. Fulfillment centers are very, very large buildings with many floors where many thousands of robots and people collaborate to fulfill your orders. And combined, there is a pretty gargantuan number of square footage dedicated to housing and serving your orders. And Amazon Robotics employs more than 1 million people worldwide. So it is actually a very large employer of associates. This is an example of a fulfillment center. In fact, this is a storage floor. Here you see these yellow things. I'm going to pause the video so I can explain properly. These yellow things are what we call pods. They are essentially shelves which contain items. These are the items that you can order, from your shaving cream to your iPhone or some book. Everything is, or the vast majority of the inventory that Amazon sells is housed in pods just like this in one of the many hundreds of fulfillment centers and storage floors therein. So the key innovation that I was saying, the key innovation that Kiva brought to the world of automated warehousing was the fact that it is no longer people who travel to the shelves, but rather the shelves that travel to people. So here you're seeing a few snapshots, a few clips of these shelves that are moving. They're not moving by themselves, they're moving because a robot has docked underneath the shelf, lifted it up, and is ferrying it to wherever it needs to go. These shelves are they are picked by either robots or human pickers and associates on the periphery of these floors. So this is an image here, or a clip of what's happening at the periphery. These pods here are being queued up at stations. I don't know if you can see my pointer. If you can, anyway, here on the periphery, you see stations. Behind these stations, there's someone who's picking things from the pod. And these are queues of pods lining up at the stations. Now, as you can see, the situation gets pretty congested pretty fast. This video was not taken in a moment of particular congestion. But there are peaks and troughs in how much traffic goes on these floors. This is really what you'd call an average day, I guess. But during peak period, which occurs typically around Christmas, for example, you will have a lot of orders being processed at these fulfillment centers, and and therefore a lot of traffic going on. I see there's something in the chat here. Oh, yeah, great. I'll keep pointing. Thanks. By the way, I'd like to say that if anyone has questions, please feel free to interrupt and jump in directly. I won't be able to read the chat right now, so if someone else is monitoring that, that'd be good. But otherwise, just jump in and ask a question. I'm happy to take them online. So this is what a storage floor in a fulfillment center looks like. Another thing I'd like you to notice here, and this will become important a bit later, is that You see items here. There's a bit of everything in these shelves, right? There's what seems to be books here. Here there seem to be some kind of flask or bottle. So there's a very large variety of objects stored in these shelves. Okay, and of course we keep track of where objects are in the shelves, where items are. But it's important to note that that the vast majority of everything that is sold by Amazon is maintained in this way. Now, in order to run such a system, we have different processes in play here. And there are, in fact, a set of science problems that we deal with as researchers at Amazon Robotics, and they're all kind of intertwined. So let me go through them. So, of course, we have a task allocation problem, the problem of generating work for these robots. Task planning, so deciding, which robot does what, scheduling these operations, allocating resources to these operations. A resource, for example, is a robot, right? So once you know that you have to pick a certain item from a certain pod, well, in fact, first of all, you have to figure out which pod it is you're picking the item from, but then you have to allocate resources to this picking operation. And this includes deciding a robot that will go pick up this pod and bring it to a picking station. You need to schedule the use of these items, of these robots. You also need to schedule the pod, perhaps. Specifically, imagine that you're ordering a razor and shaving cream, right? And the razor is in some pot over there, and the shaving cream is in some pot over there. And they're two different pods. Ideally, you want them to somehow arrive at the same time or together, or in such a way that they can be combined into one package since you've ordered both. Now, this problem has, or this requirement, it's not really a requirement, but this preference has very large ramifications across allocation, but also movement. Speaking of which, movement is obviously a very important problem to Amazon Robotics. How to move a large amount of robots sharing such a tightly contested space, a tightly packed space, without causing major congestion. So here enters multi-robot path planning, multi-robot pathfinding as we know it, coordination, robust execution. These are all science problems that we deal with. It's not all about multi-robot pathfinding, as we will see. There's a bit more to it than that. And there are a few assumptions that are made in multi-agent pathfinding competitions, such as the one that we're talking about here today, that are not entirely reflective of the robots that we have in the real world, but that's okay, and we'll maybe comment a little bit about that later. Obviously, there's a perception problem. Not so much for the mobile robots that I've shown you in the previous video, but when it comes to interacting with individual items and with packages, you need to perceive packages, you need to be able to pick them up, manipulate them, scan their destination. And the same thing holds for items. As we go towards automation of item picking and item related workflows, you need to be able to recognize arbitrary items, books, bags with clothes inside, boxes full of pencils, whatever, you name it. You have to be able to recognize them, you have to be able to pick them, and you have to be able to do so without damaging them. And I'll get more into that a little later. There's obviously the manipulation challenge, which I partially alluded to here. Perception and manipulation go very strongly together. You need to perceive to manipulate properly, and as you manipulate, you change the perspective of what you're perceiving. Finally, simulation, very important in Amazon Robotics. With such large scale, we cannot afford to go and build something and then see that it won't work, that doesn't work, or adjust the design too much. We need to measure twice and cut once, essentially, right? We need to be able to evaluate our ideas before deploying them at scale, before even often putting in place a product, right? So realizing them into something that can be rendered a product. And that is why simulation is so extremely important for us. All of these things somehow relate to the competition. There is an analog of all of these science problems, if you will, or many, not all, but many of these science problems in the competition. And my intent here for this talk, my intention is to bring up more problems than the competition deals with today, but simply to broaden the perspective so that you recognize what subset of the problems that we deal with at Amazon Robotics are in fact in focus in the competition, which ones are not, and which ones might be in the future, and that might get a nice conversation going. So let me start from work scheduling. Now, as we'll undoubtedly discuss later on when we talk about the next edition of the competition, work scheduling is an important part because it defines the multi-agent pathfinding problem that you're dealing with, right? So at Amazon Robotics, work scheduling means deciding or optimizing resource allocation in order to maximize throughput, right, and meet shipping deadlines. What this means in practice is that we have stations where, for example, items get picked from pods. We have constraints, maybe relating to deadlines. So you have to pick this item by a certain time because otherwise it won't make the truck that's going to your city on time, and therefore you won't get it today, but you'll get it tomorrow, and this costs Amazon money whenever it's late. Work scheduling also means determining which pod an item comes from. So you can imagine we have many exemplars of that shaving cream that you ordered, or that book that you ordered in, across the floor in different pods. Which one am I going to use? Am I going to send this robot to pick that item that you ordered from that pod, or another robot to go pick it up at another pod? So these are all a part of the optimization space. And of course, you have demands, right? So the items that are being ordered right now. And this is, of course, an online problem. Amazon is open 24/7, right? You open your app and you order something. And once you order, things get put in motion, and we have to be able to respond to that with our work scheduling algorithms. The result of work scheduling are assignments that determine what to pick and where. And these assignments then, in turn, update the state of the warehouse and lead to a cascade of many other things happening. Now, what's interesting here is that this is an enormous discrete optimization problem, even if we're just considering one particular floor. So it's really a gigantic discrete optimization problem, and we're not even touching the issue of movement yet. Movement comes into the picture already, though. I'd like to really emphasize this, because figuring out whether a particular robot should go get your book from, or bring this pod that contains a copy of the book that you ordered and bring it to that station, or some other combination of robot, pod, and station, well, that depends very much on what we expect travel time to be for that drive, for that robot. And travel time, in turn, depends very strongly on congestion. And so work generates MAPF problems. MAPF problems lead to congestion, which in turn affects work scheduling. So this is all extremely intertwined. So one very relevant research question here is how to adapt and rethink robotic work scheduling for new business use cases. So one of the business use cases, one of the important issues that we have in our business is to reduce the time to delivery, going towards 1 day or same day delivery. And this is, of course, a very tall challenge when it comes to dealing with such enormous optimization problems. So let's get to the moving part, the part that a lot of you are here for. Multi-robot path planning, coordination, and robust execution. Let's see what that's about. Well, of course, the floor, and here again, we're still talking about storage floors for now. I'll get into other types of floors soon. These floors store pods in areas. These are, you could assume they're sort of like blocks, and there are travel. There's a travel. There's a mechanism that, or there's a layout of such blocks that permits pods to be taken to any station via travel lanes. Another thing that I haven't mentioned so far and that I should at this point mention is that insofar as these robots that you're seeing here are concerned, so the vast majority of all Amazon robots, they operate on what we call a structured field. Structured field is basically a system of markers on the floor that allows robots to navigate along a grid, right? This somewhat simplifies the localization problem. So you can assume that robots know where they are because at all times they see these markings on the floor. I won't get into what these are physically. It's not too important for this discussion. But this sort of eliminates the localization problem or greatly simplifies it. But of course, it constrains robot movement to occur on a grid. Um, um, this, in turn, is what makes our problem so close to what you would call a multi-agent pathfinding problem. As I was saying, robots go and pick pods and bring them to stations. So, for example, here, this is a tiny example of a robot that needs to go and pick a pod and then brings it to a particular station where the item will be picked. Once pods are brought to stations and items picked from them, they are brought back to storage. And of course, identifying the pod that you need to bring to the pick station and also the storage location where you're going to put it back is all part of the space of possible optimizations you can make. There is no real need to bring a pod to the place where you had fished it out from in the meantime. That place might be filled with another pod. So placement is somewhat decidable online. Now, a key problem here is that many robots are doing this at the same time. So coordinating movements to prevent collisions is a very important problem here. This is obviously something that looks very similar to a lifelong multi-agent pathfinding problem. It is similar to this problem, but not one-to-one with this problem for several reasons. One of the reasons is obvious, and that is that these robots have a certain dynamics to them that we assume away in the classical multi-agent pathfinding problem. So a robot like this is carrying a significant amount of weight. It goes up to a certain maximum speed, and of course it has an acceleration and deceleration profile, which is specifically studied so as to maximize the ability of robots to go fast where possible, but at the same time preserves safety. And preserves the safety in terms of the stability of this whole construction on top of the robot, which can be very heavy. The other thing for which, the other reason why this is somewhat different from the multi-agent pathfinding problem is that robots in our warehouses have the ability to follow each other and follow each other at very short distances. It is not an episodic environment as the multi-agent pathfinding environment is assumed to be. Robots don't all move synchronously one step, right? So there's some non-trivial dynamics going on there. But there's another reason why the robotic movement in our floors is different. And that also has to do with the way work is generated. So you can imagine that in a large warehouse, you will have robots, you will have tasks that are generated according to some kind of distribution, right? So you will have what we call, for instance, hot pods and cold pods. Pods that have items that are frequently picked and pods that have items that are infrequently picked. You will, in other words, have certain distributions of work across the floor and across stations. In fact, picking stations and stowing stations exist, and this adds another dimension to the problem, right? Sometimes pods are brought to a station because an item has to be picked, but in other occasions, as these pods get emptied, they have to be brought to stowing stations to be replenished. So This generates a sort of work generation profile, or if you will, distributions of work that are not trivial and not entirely random, as is often the case in simulated systems like the one used for the multi-agent pathfinding competition. So, in a nutshell, that is how movement works on storage floors where we move these pods. There are other types of floors where we exploit robots that move on a grid. In particular, these are called sortation floors. In sortation floors, we have robots that carry around, as you're seeing here in the video, individual packages. We use robot floors to achieve sortation. What that means is you can imagine there is again, a square floor with, let me go back to there. Maybe here, there. There is a square floor, and you're seeing a very small portion of it in this video here, where there are, in the middle of the floor, there are these holes. These are actually chutes. Each chute is associated to a range of zip codes, and a package needs to be brought from the perimeter of the floor where there are robots or people who load these packages onto these robots. And they have to be brought by these little robots you're seeing in the video here to the appropriate chute. Below the chute is below the chute is a go-kart that accumulates these packages, and then the entire go-kart is put into the appropriate truck and then shipped out to the appropriate downstream sortation center, distribution center near the city corresponding to that zip code range. So here we also use the same sort of platform, a platform where that again moves on this grid of fiducials. The goal is to sort a stream of packages to hundreds of destinations, and we use these robots to do it. An open research question here is how to solve large multi-agent pathfinding problems in very few seconds. Just like in the other floor, here movement is an issue. Now, so hopefully I've given you an idea that for problems that are very close to the multi-agent pathfinding problem, we have a significant amount of open research questions to solve that regard movement. I'd also like to broaden our horizons a little bit in this discussion towards what we call free-range robots. Now, free-range robots, as opposed to the robots we saw in the previous videos, are robots that are truly autonomous, robots that move around in free space and have a full sensor stack and act just like all those autonomous robots that are developed in or that are seen typically in academic labs. These robots, their first use case is for the outbound dock. The outbound dock is a place where packages are accumulated into go-karts, and go-karts are brought full of packages are brought into the trucks. And these robots ideally are meant for the purpose of automating the transportation of these go-karts to truck loading areas. Now, the key challenge here is that as opposed to the previous types of floors, these floors are not necessarily marked. They are not grids. These are floors where robots are able to move in free space, as you can see here. An additional challenge is that on these floors, we want people to be present. In fact, people are present, and people do contribute to moving these carts around. And so it's very important for us to develop an autonomous robot that can operate safely around people, and that is able to be dispatched to perform a certain task just as well as a person could be dispatched to perform that task. And the challenge here is to how to balance the autonomy of these drives, so the ability of these drives to react to contingencies and efficient coordination of these drives. Again, we're targeting applications where we have hundreds of these drives, but this time working alongside people. Human safety is always the top priority, and human-robot interactions must always be safe, of course. So now, to conclude, and I probably should start wrapping it up here, anyone could tell me how I'm doing on time, I think maybe another 5 minutes. Would that work? And if there are any questions, please bring them
Yep,
on.
that would be fine. Federico, go ahead.
Okay. So I'd like to give you an example or a couple of intuitions as to what is important from the on the periphery of the movement side of things and the allocation side of things. And that involves perception and manipulation. So for perception, I'm going to whiz through this. Of course, segmentation and localization is a big, big deal at Amazon. Here I'm showing you examples of segmentation, local and identification of packages because we actually pick packages with robotic arms. This is somewhat of an old example. More interesting and more important for today is perception of individual items and the use of machine learning models to identify individual items and figure out how we can best pick an individual item, so not necessarily packaged in a box, so as to minimize the possibility of damaging the item. Bin detection is another interesting area, but I will skip this in the interest of time and zoom over to manipulation, which is more interesting for the purposes of this talk. So in terms of manipulation, we're interested in picking items and objects and packages. And the way we do things at Amazon is we start with the problem that's slightly easier. So in particular, picking packages seem to be an easier problem than picking individual items. The reason being that there is only a finite number of package types. And so this led to our first foray into robotic manipulation, which was done for the purpose of picking packages. Here in the video, you're seeing robots in production using the algorithms that we've developed to robustly pick packages and place them on drives or robots that are operating on a sortation floor. Now, the challenge here, I mean, this seems easy. Admittedly, if you have to do it once or a few times, it is easy. It could be done with off-the-shelf technology, but it is certainly not easy at the scale of Amazon. And the reason being that this needs to be super, super reliable. It has to work 99.95% of the time. So developing this technology allowed us to sort of hone in on the manipulation, path planning, and control capabilities that we needed in order to robotically pick and place packages onto robots. It allowed us to deal with a diversity of shapes and weights. Consider a package could contain stuff that's light or stuff that's really heavy. Clutter, because packages might very easily get cluttered on these conveyor belts, and we sort of got through that, and this is now deployed in many of our sortation floors. The next challenge here is to pick items, general item manipulation, to robotically pick and place any object into totes. Now, this is interesting because objects could really be anything. We have no control over how objects are packaged, if they're packaged at all when we get them. We have no control over the shape of objects. We have to be able to pick really everything. And now imagine using suction cups, which are by far the most universally robust way of picking or manipulate of arm tool that we could use. Imagine trying to pick a book with these. So if you pick it up from, and the book has, and imagine the book has a sleeve. If you pick it up from the sleeve, well, the sleeve will just, or the book will slide out of its sleeve, right? And that is what we call damage. Many other forms of damage exist. I'm not allowed to show you all the wonderful examples of damage that we have uh, caused on the objects we manipulate, but some of them are very compelling and lead us to have formulated this as one of the biggest research challenges we have, which is dealing with clutter while picking and understanding the affordances of the things that we pick while managing to pick quickly and not being the bottleneck in the process. Manipulation really requires putting together ideas from all areas, from allocation, from movement, from perception, and it is therefore a very hot topic here at Amazon Robotics. Finally, just a couple of words on simulation. We obviously use simulation at Amazon Robotics. What's probably interesting to note is that we use many different levels of simulation. We use system level simulators to simulate entire workflows. We use statistical simulators where we can uh, replace some physical simulation with statistical surrogates with basically uh, probability distributions. Um, eh, Actually, it's really important to deal with simulation in this sort of tiered fashion and go from high level simulation all the way to realistic simulation. The more you go towards realistic simulation, the slower the simulations are, and the smaller the scale at which you can simulate. But nevertheless, it is important to tick off the simulation box and to really measure twice and cut once and do simulation at all levels of development, from initial concept exploration all the way down to deployment testing. And this is a key challenge at Amazon Robotics. We have entire teams dedicated to maintaining the many simulators that we use. There are new frontiers that are worth noting, and here I'd like to call this out because this does have an impact on the kinds of challenges we'll be looking to solve in the areas of allocation and movement. So cycle time is defined as the time between when the order arrives and the order departs from the fulfillment center. And we are interested in lowering the cycle time. So this is the customer promise, right? And initially, we had a 2-day cycle time, a 2-day customer promise. We want to narrow it. We've narrowed it down to a day, and we want to narrow it down further to 1 day or same day into minutes. Now, this requires a bunch of things to happen. It requires changing the way some of our processes work. It requires building new types of warehouses. But key to this is scheduling robot operations to pack out orders in minutes instead of hours. So it all boils down to this. Um, the quicker you can get orders out the door or packed into packing, the more likely you are to be able to achieve 1 day or same day delivery. And this has an enormous impact on customer satisfaction, of course, and on our bottom line, clearly. So this is challenging because very low lead times um, um, uh, are very difficult to optimize with, right? And there's no buffer to absorb any uncertainty or variance. If you have a surge in requests on a Friday for some reason, you're less likely to be able to deal with it if you're cutting out all the redundancy from your processes, if you're promising such tight deadlines. This is a challenge, and it really reaches all the way down to the movement and to the way in which we manage to move drives or robots through our floors efficiently without causing congestion. So it really all boils down to that. So many open science frontiers at Amazon Robotics. Can we fulfill customer orders in hours instead of days? Can we scale coordinated path planning at high robot densities, really high robot densities? Can we enable human-aware motion at scale, important for the autonomous robots? Can we leverage machine learning and computer vision techniques to enable safer human-aware behavior? In a manipulation space, can we robustly identify and pick millions of items that we deal with? And finally, in simulation, how can we use simulations more effectively to test new ideas? The League of Robot Runners competition is important for us because it provides a way for the academic community to engage on some of these ideas, the multi-agent pathfinding being the core of it. But other processes are becoming more important, and next year they will feature in the competition. For example, task assignment and work generation to some extent. Everything that the scientific community does in this field is of interest to us, and that is why we are continuing to engage with the scientific community on this competition. I would like to call out also there are several scientific resources and other modes of collaboration that we're open to. There's the robotics research area, which sponsors a Amazon Research Award. There are internships and jobs available at Amazon and research grants, and these are the URLs to find out more about these. And with that, I'll thank you very much and take any questions you might have.
Thank you, Federico. What a wonderful talk. We have some time for questions. Who would like to get us started?
Okay, can I go with the first question?
Sure.
So regarding the free range robots, I'm wondering, are all the computation like on just on the computer, just on the robot, or there's still some sort of like trajectory assignment, but the robot is only like responsible for avoiding the collision with humans and deciding how it should follow the trajectory and how it should avoid human, or it's like fully computed on the robot just start and go location and it figure out everything itself.
That's a good question. So let me answer your question. I'll answer it in a somewhat indirect way because I can't tell you exactly how we're doing things, but that's not even very interesting because the way we're doing things now is not the way we necessarily need to do things, right? Or want to do them in the future. Here's the problem. We want these autonomous robots to be autonomous, meaning we want them to be able to um, navigate around people or with people, I should say, with people operating in their environment. We want them to be able to deal with things that are placed in the environment which are not mapped. And this happens often. These go-karts that they bring around might be left somewhere, right? They're not even well tracked sometimes. And although you might see that as a deficiency in our overall, warehouse management system, really it's not because we don't want to have to control everything. If we have people moving these go-karts around, they're able to negotiate with this. They're able to deal with misplaced go-karts, pallets that are lying around, and other people and traffic. So we want robots to be autonomous from that point of view. And this means gauging the situation they're in and being able to alter their paths. So not we're not talking about a sort of trajectory following controller that's just trying to minimize discrepancies from a reference trajectory. We're talking about more sophisticated behavior that you would do with model predictive control or something like that. But at the same time, we want this behavior to go beyond just preserving the ability of a robot to get around. We want it to be cognizant of the other robots in the environment. So we want to be able to solve the coordination problem as well. And we want to be able to coordinate robots at a high level, so have control over the scheduling of robots through space, right? But at the same time, preserve leeway for the robots to deviate from these schedules or from these reference, you could call them, envelopes. So it's tricky. And the challenge really is to figure out how to balance autonomy of robots to deal with increasingly complex situations and the efficiency that we gain by centrally, planning and managing what the robots do and where they go and how they yield to each other.
Thank you very much.
Other questions for Federico?
I have a question.
Sure.
Sure.
About the fulfillment aspect. So I noticed that in the pods are in a grid formation that where the interior ones are not exposed to the aisles directly. Is there some kind of auxiliary task that sort of puts the retrieves the inner pods, or is it like a direct is it done, by the robot that needs to retrieve the pod on the interior?
That is a great question, Kathy. Thanks for asking, actually. So the answer is yes. There is an auxiliary task, you could say, that is what we would call a dig out, right? How do you dig a pod out of its block? And this is, of course, a source of traffic, if you think about it. If you need to dig something out, you're going to cause traffic because you got to put the pods that you remove in order to be able to dig out the target pod, you put them in circulation. And maybe you're putting them in circulation with other robots, right? So that then you can send a robot to dig that one out. It's not too important how we do that. But the key point is that it causes traffic, right? Congestion somehow. And so a mechanism to manage such dig outs is important. And we have developed a mechanism which I can't tell you the details of right here, but it does address the problem of limiting traffic due to the need to dig a pod out, right? And it minimizes the amount of the effect that having to dig a pod out has on the rest of the floor. And there are many, many ways, if you think about it, in which you could solve this problem. And this is a very important, interesting problem for us to solve. We do have, in fact, a couple of solutions to this problem that have made us gain a lot of efficiency. But we're very open to the scientific community engaging with this problem because it's a hard problem, actually.
Yeah, I have actually a follow-up question on that. Yeah, so I suppose some of the stuff inside would be like low traffic items in some sense,
Mhm.
or is it, or it just doesn't really. Again,
So
I don't
there
want
is
to.
no, don't worry. I'm, it's ask all the questions you want. If I can't answer, I'll tell you, but it's not a problem. If you think about it, here we have here we have a lifelong problem, right? And so it's kind of natural that pods that are hot end up being in places that are accessible. Because whenever if you take something from a hot pod and that pod remains hot, you're going to access it frequently, and so it'll end up in places that are easily reachable because we certainly don't intentionally bury pods very deep into storage. We let sort of statistics take care of that, if you see what I mean. So you could think of active strategies, of course, to maximize the probability of not having to dig out a pod that is used frequently. But there's a downside to that, and that is you would have to plan at a level of granularity which is probably a bit too high because we have millions of items in a warehouse, in one floor of a warehouse. And you can never predict when these items are being ordered and the schedule at which they'll be replenished and all of that. So it's hard to make this
Okay.
to make it work
Yeah.
the way you're suggesting.
Yeah, I mean, I can imagine like several ways, right? For example, you kind of like you do a circular kind of shift, but then you will avoiding leaving a hole in the middle, but then you will put some hot items inside there. I mean, per se, right? That's why I have the question. But yeah, thanks.